Imagine a fleet of autonomous machines, each the size of a city, sweeping across the heavens, harvesting every ounce of metal, gas, and crystal the solar system hides. Picture Earth's fragile biosphere, swaddled in a thin veil of atmosphere, contrasted with the cold glitter of the asteroid belt, the searing surface of Mercury, the endless storms of Jupiter. In the next minutes, we will trace that fleet from the moon's dust to the heart of Neptune and discover what truly limits humanity's reach among the stars. Hidden beneath the dust of the moon, the iron-rich regolith of Mars, the metallic cores of countless asteroids, lie trillions of dollars worth of silicates, nickel, platinum, helium-3, and exotic gases. Yet the human body is a delicate vessel, vulnerable to cosmic radiation, microgravity, and the months-long voyages required for traditional mining. Only self-replicating, AI-driven factories can bypass our biological limits and turn the solar system into a boundless resource bank. The first step begins at the very doorstep of our world. On the moon, three-dimensional printers anchored to the regolith continuously scoop silicate, iron, titanium, and aluminium. Powered by compact nuclear modules, they operate without a single human crew, feeding raw material directly to orbital habitats. On Mars, autonomous rovers drill into iron-rich basalt without water, using impact-dry drills that fracture the crust and deliver ore to shipyards orbiting the planet. Closed-loop processing under AI-controlled temperature gradients turns raw rock into structural components, all while the red planet remains untouched by human life. Beyond the inner sanctum of the moon and Mars, the sun's furnace beckons. Mercury, scorched to 430 degrees during its day, is surveyed by thermal drones clad in heat-resistant ceramics. Solar laser cutters vaporize surface layers, exposing graphite and magnesium, which are then launched by electromagnetic catapults to a Mercury-orbiting refinery. Higher in the sky, at 50 kilometers above Venus's crushing pressure, floating Zeppelin factories glide through an atmosphere of 75 degrees, where sulfuric clouds are thick but the temperature is tolerable. These aerial factories extract metals and carbon dioxide from the dense air, feeding a network of orbital smelters. If this vision is opening new horizons for you, hit that subscribe button and let's keep exploring together. The next chapter of this grand endeavor unfolds in the belt of wandering stones that circles our sun like a glittering necklace. Here, the ancient remnants of planetary formation drift in silent procession, each a compact repository of iron, nickel, platinum, and even traces of gold. Swarms of autonomous miners, their hulls coated in reflective alloy to deflect the relentless solar wind, converge upon the most massive of these relics. The asteroid known as Psyche, a world of pure metallic heart, becomes the focal point of a coordinated ballet. Robotic arms, guided by a collective intelligence that processes terabytes of data in the blink of an eye, embed shaped charges into its crust. When the charges detonate, the asteroid shatters into a cascade of fragments, each one captured by ion-driven tugs that shepherd the debris toward orbiting crucibles. Inside those crucibles, self-replicating furnaces melt the raw ore, separating precious metals from silicate waste with a precision no human hand could ever achieve. The artificial mind that orchestrates this symphony calculates optimal trajectories, avoids collisions, and continuously refines its own algorithms, turning the asteroid belt into a factory that never sleeps. Beyond the metallic heart of the inner system, the giants of gas and ice loom, their massive envelopes promising a bounty of volatile fuels that could power a civilization for eons. Around the colossal planet Jupiter, fleets of siphon vessels glide just beneath the swirling clouds, their hulls aligned with magnetic collectors that draw in hydrogen and helium from the upper atmosphere, compressing the gases into cryogenic tanks before the turbulent storms can tear them apart. The harvested hydrogen, once refined, fuels the fusion reactors that power the entire network of orbital habitats, while the helium, a rare isotope prized for its stability, feeds the laser arrays that cut through asteroid rock, orbiting the icy moons of this giant. A new generation of explorers descends. On Europa, slender submarines, insulated against the crushing pressure of a frozen ocean, drill through kilometers of water ice to reach the liquid sea beneath. Their drills release pockets of water rich in oxygen and trace minerals, which are then pumped back to surface stations and transformed into propellant and building blocks. Enceladus, with its geysers of vapor, offers a similar bounty. Robotic harvesters capture the plumes, condense the water vapor into fuel cells, and store the resulting hydrogen for later use. Further out, the hazy world of Titan presents a landscape of liquid methane and ethane. Floating platforms, anchored by tethered thrusters, skim the seas, pumping the hydrocarbons into processing units that synthesize advanced polymers and high-energy fuels. Each of these operations feeds a growing lattice of energy distribution, linking the outer planets back to the inner sanctum of the solar system. The outermost giants, Uranus and Neptune, reside in the cold darkness where sunlight is a faint whisper. Yet even here, the promise of resources persists. Autonomous probes, equipped with cryogenic compressors, skim the upper atmospheres of these ice giants, drawing in nitrogen and hydrogen in a continuous stream. The captured gases are stored in insulated tanks and ferried by solar sail barges to distant refineries. In the depths of Neptune, where pressure mounts to unimaginable levels, experimental drills pierce the mantle, releasing pockets of crystalline carbon that have been forged by the planet's own crushing weight. These carbon crystals, essentially giant diamonds, are harvested and transported to orbital workshops, where they are cut into lenses for high-resolution telescopes and into superconductors for quantum computing cores. The very act of extracting these treasures reshapes our understanding of planetary interiors, turning the distant ice giants into active participants in a solar-wide economy. All of this material, refined and repurposed, converges toward a singular, awe-inspiring vision: the construction of a megastructure that would eclipse the sun itself. Countless tons of metal, carbon, and exotic alloys are assembled into a lattice of solar collectors that encircle the star, forming a Dyson swarm of unprecedented scale. Each collector, a thin sheet of graphene-reinforced silicon, captures photons and converts them into pure, uninterrupted energy. The swarm is not a solid shell, but a dynamic ribbons that adjust their orientation to maximize output while maintaining stability. The energy harvested by this artificial halo is beamed back to Earth and to the myriad colonies scattered across the system, providing limitless power for propulsion, manufacturing, and even terraforming. Imagine a world where the constraints of scarcity have been erased, where humanity no longer looks to the heavens with longing, but with ownership. The very fabric of civilization would be rewoven, its threads drawn from the raw wealth of the cosmos. Yet, as we contemplate this boundless abundance, a deeper question lingers. What becomes of a species that no longer needs to struggle for survival? Does the removal of scarcity elevate us to a higher plane of existence? Or does it strip away the very challenges that have forged our identity? The answer, perhaps, lies not in the machines that harvest the stars, but in the choices we make once the harvest is complete. The path we have traced from the dust of the moon, through the rusted plains of Mars, across the scorching deserts of Mercury, into the acidic skies of Venus, through the glittering corridors of the asteroid belt, and finally into the swirling storms of the gas giants, demonstrates that the limits of human ambition are not set by biology, but by imagination. The autonomous fleet we have envisioned is a testament to what can be achieved when intellect, perseverance, and technology converge without the frailties of flesh. If this journey through the future of solar system mining has sparked curiosity, share your thoughts in the comments below. How would you envision life in a civilization powered by a Dyson swarm? And if you wish to follow the next steps of this speculative odyssey, consider subscribing and turning on notifications so you won't miss the chapters that lie ahead. The stars await, and together we can continue to explore the possibilities that lie beyond our fragile blue world.